Assalamu alaikum, and thanks for attending. So, I present myself. So, my name is Dada Mohammed Abdurrahman. I'm a petroleum engineer working for Sonatrach, which is a joint venture part of Sonatrach, ENI, and Equinor. Before starting, I wanted just to open a bracket. So, this is with regard to the party that is happening there. So it happened this morning, yesterday. I think this is unacceptable and does not reflect the values of NAPEC, and hope if there is anyone from NAPEC hearing this message, or if anyone can forward this message to them. So close the bracket. So the topic I'm going to speak about in these couple of minutes is about how to leverage machine learning capabilities to improve overall performance of oil and gas exploration and production activities. So this presentation is structured as follows. I'll start by an introduction, then I'll speak about what is machine learning about. After that, we'll see what kind of initiatives have been undertaken by researchers to deal with the application of machine learning in EMP problems. Then it will be the turn of ongoing machine learning-based industrial projects. And at the end, I'll finish by a conclusion. So, let's get started. In a highly competitive environment, innovation has always been the key for oil and gas companies to address market demands, generate or maximize revenue, and maintain a high level of competitivity and leadership. Industrial operators, especially those dealing with oil and gas, have now adopted machine learning solutions because of their considerable potential in solving a lot of and wide, complex and interrelated challenges, as well as delivering key insight to decision makers in quick times and with a high level of uncertainty. Low level of uncertainty, high level of accuracy. So this has been made possible thanks to the massive amount of data accumulated over time, the rise of the development of data transfer systems such as Internet and Internet. So the development of IT infrastructures, newly servers, computing-powered cloud solutions, and the advent of big data solutions. Many experts have the vision that machine learning will play a pivotal role in shaping the future of fossil fuels energy and driving significant progress within EMP activities. For instance, according to McKinsey, machine learning and big data applications could help carbon industries save up to $50 billion in the next decade, while others noted that if the hydrocarbon industry succeeds in applying machine learning techniques in its EMP disciplines, savings in terms of time and associated costs will be significant. The choice made by oil and gas companies such as Gazprom, ExxonMobil, Equinor, or Total was a choice made by those companies. So to step into the field of machine learning is wise and deserves to be considered for possible implementation. Instead of venturing alone into this highly demanding technical domain, they have opted to collaborate with high-tech companies such as Microsoft, Google Cloud, NVIDIA, and so on. So this strategic choice has led to outstanding achievements, and a lot of expertise have been gained by their researchers and engineers. The aim of this presentation is to show to the Sonatrach managers, engineers, I hope there are some of them here, see how, what kind of topics can be solved using machine learning solutions, and what's the best way forward to implement it as part of an industrial project. What's machine learning? Machine learning is another way of solving problems using data without a priori knowledge of the physics or the logic behind that problem. It relies on some concepts of statistics to deliver insights and extract meaningful insights and information critical for decision makers. Yeah, that's it. So there are many categories in machine learning. First, a popular one is called supervised learning. In supervised learning, we try to find a correlation between inputs and outputs. And from it, we can build predictive models. This can be done by generating regression models or classification models. The second one is called unsupervised learning. In unsupervised learning, we perform a thorough exploratory data analysis to extract or to get or see how data are related between themselves and to extract or to get hidden patterns. The third category is called reinforcement learning. This is new in the machine learning family. It's all about doing optimization. Here, so a learning algorithm try to find the best solution in order to maximize an objective function. It was first developed for robotics and autonomous systems, and has been applied in EMP problems such as field development, planning, assisted history, matching, and characterization of fluid flow in subsurface. Machine learning solutions can be implemented or are solely implemented using programming with languages such as Python, MATLAB, Algeria, or C++. They can be implemented in premises using internal capabilities or through the cloud, through platforms proposed by Microsoft, such as Azure ML, Google Cloud, IBM Watson, NVIDIA, and so on. Having said that, let's now move on to see what kind of researches have been performed to solve EMP problems. With regards to geosciences, we all know that feedback from geoscientists is critical to have or to perform quality assessment of the prospect under investigation. So, among those feedback is feedback from geophysicists. So, geophysicists are the key in here, as they provide us with a first picture of the reservoir, how layers are structured, and where potential hydrocarbon traps are located. Geophysicists may deal with seismic data having missing traces or blurred traces. And here come the advantage of using a particular type of neural net called generative adversarial networks, or GANs, to perform image reconstruction. It's always noteworthy to mention that GANs have also been applied to perform assisted seismic inversion in order to predict a lot of characteristics or properties of the rocks and reservoir. GANs have been developed by A.M. Goodfellow, who was head of research at Apple and Facebook. They are designed to create stunning and synthetic images from real ones, often indistinguishable from real ones. So, GANs are composed of a generator and a discriminator. A generator tries to generate images or pictures from scratch, then gradually refine them in order to get increasingly realistic images. While for the discriminator, and the two works in parallel, the discriminator works as a classifier and tries to distinguish between realistic images and fake images that do not reflect the properties of raw images. What we see here on the right is a work performed by the authors here, Oliveira and Ferreira. They have deliberately eliminate some parts of some pictures. They perform their training, they test their model, then they applied their model using two approaches. And what we see here below is the output of their model. What we see in the left below is by applying a single network, a single GAN. While what we see in the right is by applying a series of GANs. And look here, the two one are really looking to the initial one here that is up in the left. Another type of neural networks called convolutional neural networks, or CNN, were proven to be really, really powerful with regards to the identification and delineation of salt bodies or faults. CNNs allow to delineate or allow to delineate images, objects of interest within an image. Using CNN, we can easily characterize or locate dome salts or faults within an image. We can use CNN to build regression models as we see here. So the upper row is the initial images done manually or using classical models. What's in the middle is by applying a simple algorithm called support vector machines, and what you see here and below is using a CNN, and look for the difference when using SVM or CNN. When using CNN, it's really the same as the initial images. So we can use CNN to build a regression model and to perform, here the regression model allowed to perform image-to-image translation. It's to say, predicting an image from an image. An example of this application is predicting sinusoids or dips in subsurface images. This example is what was part of a competition proposed by Schlumberger 2 years ago, and the objective was to predict dips from resistivity logging images. We can also build a classification model to state whether a particular pixel or contour of an image is likely to hold a fault or not. And what you see here in the right is a work performed by Wu and Shi recently, early 2018. So here, the raw image is what we see here in image A, on top of the picture. What we see here in C is the interpretation of faults using classical or analytical models. What we see below is using ACNN, and look for the difference. When using convolutional neural networks, we can perfectly identify and locate faults with less uncertainty. Look when using classical model, image C here. So some parts of the picture are blurred. We cannot distinguish if it's a fault or a potential trap of hydrocarbon. Still, with reservoir characterization, so simple algorithms such as SVM, decision trees, random forest have been applied to perform facies classification and petrophysical characterization using logging data structured in tabulated format. These kind of algorithms outperforms the classical models used by petrophysical engineer to perform an interpretation. With regards to drilling and completion, a lot of machine learning models, especially those dedicated to perform time series prediction, have been applied to anticipate unwanted events or and reduce non-predictive time, NPT. It will be very interesting to check the papers cited in here to see how the authors perform build their models and perform prediction to avoid problems such as kick or drill string stick in the wellbore, or start dressing in the wellbore. All using the drilling data parameters and trends of equipment that are part of any drilling or completion activity. With regards to reservoir simulation or reservoir engineering, so here I wanted just to highlight a recent work, dates back to only 2022. So here, the authors, that's before that. Here, a new type of neural network called physics-informed neural nets have been applied to perform a wide variety of reservoir simulation and field development planning, such as well location or flow or injection allocation, well placement or well or injection or production allocation. So here, pins have been designed to mimic the properties of derivatives that we usually find in any partial differential equation. The authors here simulated CO2 injection and post-CO2 injection, and they made a comparison between by applying their simulation first in GEM, which is a software built by a CMG, and then they have performed their work using the newly created or designed neural network for pins. And look here on the right, for the same results, they have been able to perform their simulation using pin in, let's say, 250 times faster than using GEM. So, really impressive. With regards to industrial projects, as I said, all the companies went for a collaboration. The first example is the partnership between NVIDIA and Baker Hughes. So this partnership is meant to harness different databases, including drilling data, seismic data, and collection data, to develop solutions for clients. The two companies claim to have developed, in terms of production, a model that is able to perform very well than the analytical models. So here they claim that they can predict if an anomaly will occur, and the accuracy is 3 to 5 times in comparison to classical models, and 4 to 5 times when an equipment is likely to fail. So, the second example is a collaboration between Total and Google Cloud. So here the partnership aims to develop solutions for geophysicists in order to get them up to speed to perform their duties, let's say interpretation, in a very efficient manner. There is no feedback from two companies with regards to any lessons learned or any result of this collaboration. The last one is collaboration or partnership between Equinor and Ambient. Equinor has chosen to deploy Ambient's solution, which is an AI solution called Infinity, in order to optimize production from their oil wells located in the Bacon field. So this solution is part of a digitalization project. You have IIoT to perform data collection and transfer. You have an Infinity to perform different optimization and then submit them to control room or anyone to perform the optimizations, optimize well production. It was reported that by doing so, by deploying the Infinity solution, Equinor was able to increase its overall oil production by 6%, as well as decreasing well suffering from overpumping by 11% strokes per minute. To sum up, oil and gas business, being a demanding and competitive business, is still relying on innovation to get to different targets and meet expectations and respond positively to the market demand. Advancement and technology have always been pivotal to the hydrocarbon companies, and machine learning emerges as an innovative optimizing tool to help them achieve different goals. The Sonatrach will surely benefit from the capabilities of machine learning solutions and as well as from the lessons learned from existing machine learning-based industrial projects. For this to happen, the Sonatrach will have to set a strategy in order to take maximum of benefits, maximum from machine learning capabilities. This can be done by establishing partnerships with tech companies such as Microsoft or Google, moving forward with the digitalization. So this year, Sonatrach has concluded a contract with Huawei. Huawei is very known to you. I don't have to tell many things about it. And as well, at the end, we have to train our engineers and experts to get strong foundation in the field of machine learning, because it's not easy to step into that field. We need to work cautiously, wisely, in order to get the most from machine learning. And thanks for your attention.